complete the reduction. Hello, welcome back. We'll just complete the reduction that we were looking at. So yeah, in the previous video, I was discussing reduction from subset sum problem, reduction from vertex cover to subset sum problem. So just to remind, so to show a problem is NP complete, so we need to show that it is in NP and it is hard for NP or NP hard. So the first step is to show that it's in NP. So use the definition of NP through small witness characterization or small witness property, and show that the given problem has small witness property, and then take some NP complete problem or NP hard problem B, and then show that B reduces to A. So there is a polynomial time transformation where every input instance of B is transformed to input instance of A, such that S answers are preserved and no answers are preserved. Okay, that is more precisely, this is the definition of reduction that we talked about. Okay, that is, we say that A reduces to B if there is a polynomial time algorithm F such that F would output strings. It's not a decision algorithm. For all X, X is in A if and only if F of X is in B. That is, output of F should be a member of B if and only if X is a member of A. Okay, so that is the definition of reduction. So we are looking at this subset sum problem, which is a kind of restricted decision version of an abstract problem. So we are given a finite set of non-negative integers and a target value t. We want to output S if and only if there is a subset x prime of x which adds up exactly to t. Okay, so it should be exactly. Okay, so yeah. So the theorem is subset sum is NP complete. So step one is to show that it is in NP. So it's a fairly easy witness characterization there. The subset itself is a witness. Okay, so the indices itself is a witness. Subsets which add up to T. If there is no such subset, then there is no witness. So the witness characterization holds. Now for hardness, we have to carefully choose a problem. So we chose vertex cover. So basically, given an instance of vertex cover, remember that vertex cover instance consists of a graph and a value k, such that we want to decide whether graph has a vertex cover of size k or not. Now, so all we need is to construct a set x and a value t such that gk is in vertex cover, that's S instance of vertex cover, if and only if xt is an S instance of subset time sum. That is, the set of integers x has a subset which adds up to t. Okay, so that is a condition. So here we just use base 4 representations of numbers basically to encode values of edges. I mean, basically encode edges as numbers. Okay, so what we do is we just we want to generate one number for each edge and one number for each vertex. Okay, so what we do is we label the vertices edges, sorry, to 0 from 0 to m minus 1 in an arbitrary fashion. Edge 1, edge 0, edge 1, etc. up to edge m minus 1, assuming that there are m edges. Now the corresponding numbers, so for each edge, edge e, the number ae is defined as 4 to the power e. So if edge e is a 10th number, then this will be 4 to the 9. Okay, so 0, it starts starts from 0. So 4 to the 10, 4 to the 0, 4 to the 1, etc., etc., etc. Okay. Now vertices, what we do is we take 4 to the m plus we add all the values of edges which are incident on V. Okay. So these are the numbers. So x is our subset, which x is our set which has m plus n elements. Okay, ae for each e in E, av for each v in V. Okay. Now the target number is k into 4 to the m plus 2 into 4 to the sum of 4 to the I, where I ranges from 0 to m minus 1. This is basically sum of the values associated with each of the edges, but twice value. Okay. So the claim is GK is a vertex cover if and only if XT is in subset sum. We just looked at the forward direction. I'll just go over it again for just concreteness. So suppose GK is vertex cover instance, that is G has a vertex cover of size K. Now I want to show that XT is in an S instance of subset sum, or in other words, X has a subset which adds up to exactly T. So the promise that GK has a vertex cover, I mean G has a vertex cover of size K. So let's start with such a vertex cover. So S be a vertex cover of G of size K, of course. Now X prime, we are taking it as the subset corresponding to S. Okay, so this is not completely correct. So I should have just written this as AV, V is in S. Okay, and then take values corresponding to those edges which are incident on exactly one vertex. So this picture explains it better. So you just look at all edges that go out of V, out of S, sorry, okay, and take the values of these edges. That is going to be our set. Okay. Now let's look at the sum of values in X prime. X prime is defined this way. So it's basically sum X prime is summation AV V in S plus summation AE. E has exactly one endpoint in S. Okay. So this is nothing but, remember that cardinality of S is K. So there are exactly K instances of 4 to them in the summation. Okay. So that is how we had defined it. Sorry, defined it here. Okay. So there are K such vertices. So we'll have K into 4 to them plus. So let's see what is the remaining. Okay. Now for each vertex, so we also have 4 to the E for edges which have at least one endpoint in S, right? But we can split these into two sections. One, those which have exactly one endpoint, one with both endpoints. So for, say, suppose UV is in S, suppose the edge is present, okay. So for this, what is the contribution that we have? So one from U's side, so when I consider AU, I'll get 4 to the E, as well as when I consider AV, I'll get 4 to the E. So that will be 2 into 4 to the E, running over all edges where both endpoints are in S. Now, but there are also edges which have exactly one endpoint in S, so that will each of them will contribute 4 to the E, where E is the label of that vertex, edge, sorry. Okay. Now, but we have explicitly taken something more here. So that is edges, values corresponding to edges which have exactly one endpoint in S, okay, or one vertex from S. So that is this summation. So these two summations, so AE is basically 4 to the E here. Okay. So this is equal to 4 to the E. Maybe I'll just erase this and make it 4 to the E. So then this adds up to T. Now if you just see, so there are exactly M such edges. So each will occur twice. So this is, so these vertices and I mean these edges and these edges, they are basically the same. The summation over the same set, right? So this is equal to T. So that proves one direction. What is it we have? So given a vertex cover of size K, we have exhibited a subset of numbers which are nothing but these, that is numbers corresponding to the vertices in the vertex cover, and numbers corresponding to edges which have exactly one endpoint in the vertex cover. Okay. So they basically add up to the carefully chosen value T. Yeah. So this proves relatively easier direction, okay, the forward direction. That is, G has a vertex cover of size K. That means X has a subset which adds up to T. We have in fact explicitly exhibited such a subset. Now let's consider the converse direction. So suppose XT is in subset sum. That is, there is a subset x prime such that sum of values in x prime is equal to t. Okay. Now, so how will x prime look like? So x prime will look like union of, so x prime will look like AV for some V subset of V prime subset union AE E in E prime for some V prime subset of V and E prime subset of V. So this is by definition. X is such a set. So if you take any subset, that is how it should be. So you would have chosen some AVs and some AEs. That is what our X is, right? X is defined to be this. So you would have taken some subset of this, some subset of this. Okay. Yeah. So now sum x, so T is equal to summation V in V prime AV plus summation E in E prime AE. Now, so remember this value is k into 4 power m plus 2 summation I equal to 0 to m minus 1 4 power I. Okay. So let's just, so see, remember that these are all base 4 representations, right? So this 4 power I corresponds to a base 4 representation. Okay. So this number you can imagine, so this number T looks in base 4 as a following. Okay. So this is 0, 1, etc., 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 m minus 1. Okay. So at each of the points, so what is the value it has? So it has 2, 2, 2. Okay. And so 4 to the m onwards, so this is k. So k is some bigger number. Okay. So whatever, log to the base of 4k many digits will be there. Okay, base 4 digits. So that is what it will be. Now let's add. So let's look at E prime and V prime. So how big, how can they add? Okay. So first claim is, so claim 1, cardinality of V prime is equal to k. Certainly it cannot be greater than k because t is equal to this, right? So this is in fact equal to, this is equal to this. Okay. So we know that this summation is equal to k into 4 to the m. So how do you get to 4 to the m? It may be contributions of 4 to the i's where I less than m, or it may be from AV. Okay. So but we know that, so clearly cardinality of V prime is less or equal to k. If not, sum x prime will not be equal to t, will be in fact greater than t, right? That is how the numbers are chosen. Now we prove that it is in fact equal to. So let's see how it is. Now let's so it's less than or equal to k is clear. Okay. So suppose cardinality of V prime is less than k. Say cardinality of V prime is k minus 1. It really does not matter. It could have been k minus 2 or whatever. The argument will hold. Okay. So then summation v in v prime av is equal to k minus 1, in fact cardinality of v prime, into 4 power m plus something. Okay, so now let's just count. Okay, so let's just count this something. Now sum x prime is equal to this number v in v prime av plus e in e prime ae, which is equal to, so I'll just write this as star star. Okay, cardinality of v prime into 4 power m plus star star plus summation ae e in e prime. Okay, now so we want this to be k into something, right? So we know that this is equal to k into 4 power n plus 2 into summation 4 power I equal to 0 to m minus 1. Okay, yeah. So now let's just see how many. So yeah, so the idea is the following. So let's just look at these. See, for each, say for example, for if I consider E, so when I take this sum, apart from this, see these are all after 4 power m, right? So position m, not 4 power m, position m in the base 4 representation. Okay, so now if I look at, so this is what here we have. So these contribute to cardinality of v prime. Now the remaining one, when you add, right, so the digit at a position E corresponds to the number of times the edge E appears in this summation. Okay, either in star star or E prime. Okay, so E prime will have at most one, right? It's a subset of edges, so it will contribute at most once for an edge. Now this summation star star, how many times will it contribute? If the edge happens to be within V prime, that is u and v, edge is uv such that u and v both are in v prime, it will appear twice. Can it appear more than twice? No. So an edge will appear only 3 times, or in other words, in this summation, for each edge the corresponding digit, that is base 4 digit, will be at most 3. Okay, so in the base 4 representation, of sum x prime, the position, so for every e, the position corresponding to e will have value less than or equal to 3. Why is that? Because if the edge, so the worst case is, the worst possibility is for an edge e equal to uv is UV in V prime and E in E prime. So even in this case, 4 to the E appears only 3 times. See, 4 to the E in base 4 representation is 1 0 0 0 0. So 1 is at the Eth location. E is 0, that means 0th location. E is 1, that is first location, and so on. Okay. So what happens is this summation, if you take every base 4 digit from position 0 to m minus 1 will have value 3. So therefore there is no overflow in the base 4 summation star star plus E in E prime AE. So yeah, so if there is no overflow, therefore star star plus E in E prime AE is less than 4 power m. Therefore cardinality of V prime is greater than or equal to k, and hence cardinality of V prime is equal to k. Okay. Yeah. So let's go back. So we started with some subset which adds up to T. Okay. So by the way we have defined these numbers, we can split the subset into numbers corresponding to vertices and numbers corresponding to edges. The first thing that we have argued is the numbers corresponding to vertices, there can be exactly k many. Okay. So certainly it is at most k. If it is more than k, then it cannot be equal to this number. It will be more than this number. So it's at most k. But then we saw that it is in fact exactly equal to k. That is because if you look at the remaining numbers here, the remaining numbers we wrote as star star plus whatever. Okay, so the remaining numbers contributed by these two, they are in fact yeah, so the remaining numbers, they will be strictly smaller than 4 to them, because if you just do this addition in base 4 representation, in base 4 every position will have a value at most 3, because the worst possibility is the edge is such a way that edge appears in E prime as well that both the endpoints are in V prime. Then 4 to the E for that edge is going to come 3 times. Okay, so in other words, in the addition there is no overflow, or in other words the value is at most strictly less than 4 to the m. Okay, so therefore cardinality of V prime has to be at least k, but obviously since it is at most k, it will be equal to k. Now what happens? So the first statement is done, so first claim is done. So the cardinality of V prime is exactly equal to k. Now it's nothing much left, right? So t is equal to this number. Okay, but then this basically says that every edge will appear. So for every edge, either it appears in this summation or in this summation. Okay, so now okay, so therefore t is, let's write it explicitly, k into, yeah, therefore 2 into summation I equal to 0 to m minus 1 4 power I is equal to star star plus summation E in E prime 4 power E. Okay, so that is for every edge E in E, either both endpoints E are in V prime, that is E is not in E prime or E is in E prime. And has exactly one endpoint V prime. Therefore, V prime is a vertex cover of G. And we have cardinality of V prime is K, so it's a cardinality K vertex cover. So this completes the argument. Okay. Yeah, so this is bit tricky, though the reduction looks bit simple. I mean, the construction is simple, but it's bit non-trivial. So let's just give an example. Okay, so let's construct an example graph. Okay, so with the 5 vertices, I will not put too many edges. Let's see. So edge number 0, 1, 2, 3, 4, 5, maybe one more edge. Okay, 6. Okay, so 7 edges. Vertices let's label as A, oh sorry, A, B, C, D, E. Okay. Now what are our numbers? So okay, so instead of A, I will just have B, C, D, E, F. Okay. Now what are the numbers? So A0 is 4 power 0, A1 is 4 power 1, A2 is 4 power 2, etc., etc. A6 is 4 power 6. Okay, these are the numbers. And AB is basically, what was it? 4 power m, m is 7, so 4 power 7 plus, what are the numbers? 4 power 6 plus 4 power 2 plus 4 power 0. So in base 4 representation, this is 0, sorry, it's 0, it is 1, 1, 0, 1, position 2, power 2, power 3 is 0, power 4 is 0, power 5 is 0, 1, 1. Okay, in base 4. Okay, AC is equal to 4 power 7 plus 4 power 6 plus 4 power 5 plus 4 power 4. I'll leave it to you to write it in base representation. AE is 4 power 7 plus 4 power 5 plus 4 power 3 plus 4 power 1. B, C, D. AD is 4 power 7 plus 4 power 4 plus 4 power 3 plus 4 power 2. A, B, C, D, E, 4, 5. AF is 4 power 7 plus 4 power 0 plus 4 power 1. Okay. Yeah. So let's take any vertex cover. So let's say, is there any vertex cover of size 1, 2, 3? Okay. So let's take case 3. Okay. So 1, 2, 3. Okay. BDE is a vertex cover. So let oops, sorry, let k equal to 3, then BDE is a vertex cover of G. Okay. Now, so let's take the sum value. So T value is what? So T value is K 3 into 4 power 7 plus summation I equal to 0 to 6 4 power I 2. Okay. Now for BDE, so let's see, let's write down. Okay. So X prime corresponding to BDE is, so what is X prime? X prime is AB, AD, AE, and what else? Those edges that correspond to exactly one endpoint. Okay, that is A1, A0, A5, A6, A4. A1, A0, A5, A4, A6. Verify AB plus AD plus AE plus A1 plus A0 plus A5 plus A4 plus A6 is equal to T. Okay. So I'll leave it to you to verify. So it should be equal to that. I hope this demonstrates the reduction. Okay. So basically we reduced vertex cover to subset sum. So hence we know that subset sum is NP hard, but we already have seen a witness characterization. In fact, I gave it as an exercise, witness characterization for a subset sum. Okay, so that means subset sum is NP complete. Okay, so this is not only NP complete problem apart from what we have seen so far. So in fact, there are other NP complete problems. So there are a lot of them. Okay, so there are a lot of them. To state a few, tree coloring. So given a graph, is there a proper tree coloring of the graph? I will not define what it is and so on. Of G. Okay, this is NP complete. It's also NP complete for even special classes of graphs like planar graphs, and then Hamiltonian cycle. Okay. Given a graph, if there is a Hamiltonian cycle or not. Similarly, Hamiltonian path. Or in fact, you can even generalize this to K cycle. So given a K and a graph G, is there a cycle of length K? Similarly, given a K and a graph G, is there a path of length K? So all these problems are NP complete. In fact, there are like several such problems. In fact, there are several variants of satisfiability. So one is circuit sat or formula sat. Okay. So instead of a CNF, if you have a Boolean circuit representing the function, is it satisfiable or not? Instead of a CNF, you just have a Boolean formula, arbitrary Boolean expression using and or negations. So all these are NP complete. So only thing is, so the variant of SAT which is not NP complete, which is in fact known to be in P, is DNF. Instead of CNF, if you take DNF, then it can easily be seen that You can check satisfiability fairly easily. Yeah, so this is only a small set of problems which are NP complete. In fact, the reality is there are like thousands of problems which are NP complete. And in fact, most of the practically relevant problems are in fact NP complete. Okay, so for example, if you look at the k-means clustering, so the clustering problem is NP hard. Almost literally any problem that you take. Okay, so many of them, only a few of them are known to be in P. Okay, so that way, so these problems are not only in NP, they are hard, and the conjecture is like, so the Cook's hypothesis or general conjecture is no NP complete problem admits a polynomial time algorithm. Okay, so NP hypothesis, so P versus NP hypothesis, no NP complete problem admits a polynomial time algorithm. Okay, yeah, so this belief, I mean, there are like lots of evidences for to believe this. So till date no one has proven it or disproved it, so we don't really know the truth about it. So but it's widely believed that this is the truth, this is a reality we have to live with. So people, I mean, particularly the algorithms community, have devised ways of coping up with NP completeness. Okay, so people try to come up with the various ways. Okay, maybe you don't want exact solution, what you want would be approximation solution. So this is a discipline of approximation algorithms. So usually there is a course with this title. Unfortunately, I don't think this is offered next semester, but yeah, it might be offered next year. Okay, then there are other ways of dealing with it. So one is through parameterized algorithms. Okay, so you will be seeing a bit of parameterized algorithms in a course by Akanksha Agarwal. I think it is a recent trends in theoretical computer science. Okay, and there are exact exponential algorithms. Particularly, instead of 2 power n, say, can I have 1.4 n or 1.1 power n and so on. So in fact, if you can prove something like 1.01 power n algorithm for satisfiability, it's reasonably fast. See, the best known is 2 power n. Okay, so now if I can improve it to 1.10 n, at practical level I can actually solve a lot of instances. Okay, so 2 power n, if I can solve up to 10 instances, say 2 power 10 or 2 power 20 maybe. Okay, so beyond that will be infeasible. Whereas with 1.01 power n time algorithm, I can solve up to 100 or 200 instances. Okay, so that way these things have practical relevance. And there are also other ways of attacking this. So one is beyond worst case. That is, don't really look for worst case analysis, maybe average case or other kinds of analysis. Okay, so these are 4 methods. In fact, there are other paradigms too, but these are the most prominent ones. In fact, approximation algorithms and parameterized algorithms, they are kind of stream algorithms now. You will see a huge amount of literature there. So beyond worst case is not kind of, I mean, it has takers, but it's a bit difficult to implement. I mean, a bit difficult to do. So this is all about analysis of algorithms. Okay, so take an algorithm and do an average case or worst case. We already seen for quicksort, it's not very trivial. It's bit non-trivial to do it, right? For other algorithms, it gets much harder. Okay, so in fact, I'm offering a course which kind of will focus on some specific aspects of this. So this is TDA. Okay, so this is I don't remember the course number, so recent trends. Okay, so this is CS6100. Okay, so these two aspects covered in the next semester. I believe the exact exponential algorithm might also be covered by Akanksha in the same course. Approximation algorithm usually was taught by either Narayana Swami or Ravishankar Krishna Swami. This year, I think it's not being offered. I'm not very sure. Okay, yeah. So that is all. So all the best for the NSEM. We'll have discussion session on probably Wednesday or Thursday. Okay, thank you.